So now we'll discuss the distance or displacement for an object accelerating from rest. Once again, going in a straight line from rest is one of the simplest types of acceleration to analyze and study. In this case, when you're going in a straight line, the magnitude of the displacement and distance will be the same, so the D here can stand for your distance or displacement. As we saw in the accelerating cart on the ramp lab, the distance or displacement graph is quadratic when graphed versus time. The general equation is going to be 1/2 AT squared, where A is the acceleration and T is the time. Now when we're doing free fall, which implies gravity, gravity is the accelerator, so you can generalize and just say, or specialize and say the distance or displacement for free fall is 1/2 GT squared, where G is our negative 9.81 meters per second squared. So that's the same equation except for you're plugging in the specific negative 9.81. The circled equation is the more general, which can apply to a car starting from a stop, a runner, a bicyclist, anything starting from rest, what its displacement will be after a given time t. Now there's another way to calculate your distance or displacement, and here's where it can get a little confusing for people because there's an alternate way to solve these problems. Sometimes the alternate way is the easier way, but the displacement or distance is the average velocity times the time. Simply, that is a reworking of our definition of average velocity, which is from our original notes. That is, V average equals our displacement over time. So you just multiply both sides by t, and you come up with the circled equation. So let's say we have an object that is accelerating, say it's a car with an acceleration of 6 meters per second squared. As we saw on a previous page, the speed, well, at time 0, if you're starting from rest, the speed is 0 meters per second. After 1 second, your speed is 6 meters per second. Conceptually, then you're gaining 6 meters per second each second, so your speed after 2 seconds is 12 meters per second. So you gain 6 more meters per second of speed each second, so you go to 18 after 3 seconds, and then 24. Once again, you could be creative with the next value, but as we learned previously, the V final, if you're starting from rest, is your acceleration times your time. So in that last box there, the final velocity is your acceleration of 6 meters per second squared times 4.3 seconds. That would be V final equals 25.8 meters per second, or if you round off to 2 sig figs, 26 meters per second. Alright, so that's a review. Once again, if the acceleration is negative, well, the speeds, we would still call them all positive, but if we were asking for the velocities here, the velocities would be negative values. But now we want to figure out the distance traveled for an object that's accelerating from rest. Well, at time 0, it hasn't gone anywhere, so the distance and the displacement is 0. But the displacement is going to be simply found with that equation, D equals 1/2 AT squared. Let me erase a little bit here and then plug the numbers in. So if you plug into that equation, D equals 1/2 AT squared, the acceleration is 6, and at time 1 second, 1/2 times 6 times 1 squared, your distance and your displacement is 3 meters. Now the interesting thing here is, and the difficult thing is, if your speed at the end of the 1 second, or at the 1 second mark, at that instant the speed is 6 meters per second. And now you've traveled for 1 second. Shouldn't you have gone 6 meters? And this can be troubling. But that's where the equation at the top of this page explains the situation, because you haven't been traveling 6 meters per second for a full second. You started off at 0 meters per second and you sped up to 6 meters per second. You're only going 6 meters per second at that time, at that instant, and you're going to be increasing your speed even further after that. But if you take your average speed over that first second, your average speed was 3 meters per second. So if you look at that equation at the top, if your average speed is 3 meters per second times 1 second, for 1 second, you go 3 meters. Alright, so now we're going to look at the 2 second mark. I'm going to erase a little bit. Okay, so now we have 2 seconds plugged in for the time, so it's 1/2 times the 6 as the acceleration times 2 squared. 2 squared is 4, times 3 is 12. So your displacement now is going to be 12 meters at the 2 second mark. Once again, if you go to the top equation, which is an alternate solution, you could figure out your average velocity for this whole time period of 2 seconds, from 0 to 2, the whole span of 2 seconds. If you increased your speed from 0 meters per second to 12 meters per second steadily, your average speed was 6 meters per second. But you've been doing that for 2 seconds. So if you're averaging 6 meters per second for 2 seconds, that equation at the top of the page here, 6 times 2 is 12. Let's go to another example, the 3 second mark. So you plug in the 3 for time. So 1/2 times 6 is 3 times the 3 squared, which is 9. 3 times 9 is 27 meters. So at 3 seconds you've gone 27 meters. Once again, you can figure it out from the other equation at the top. Going from 0 to 3 seconds, now it's a little bit tougher here. If your speed is increasing from 0 to 18 meters per second over that span of 3 seconds, from 0 to 18, your average speed is 9 meters per second, but for 3 seconds. So 9 times 3 is 27, so you could get it from that equation at the top as well. 2 more examples here. So we're getting a little fancier here. I'm using subscripts now. D sub 4 means the distance or displacement at the 4 second mark. Once again, these are all at values at that particular instant in time at the 4 second mark. So we have 1/2 times the 6, which is 3, times 4 squared. Now 4 squared is 16. Make sure you square that first. So 16 times 3 is 48 meters. Now let's do the oddball one, but in the same way. If you have a calculator, it's not a big deal. So we're plugging in 4.3 for time. Once again, it could be even more detailed. You could have like 4.37 seconds, but here we just have a two sig fig number to the tenths. So 1/2 times 6 is 3 times the 4.3 squared. Make sure you're only squaring the 4.3. Don't square the 3. Don't multiply the 3 times the 4.3 first. Square the 4.3 first, and then multiply that by the 3. And it comes out to be 55.47, but we should round that off to 55 meters. So there you have it. That's how you figure out the distance or displacement for an object that's accelerating from rest. This only works if you're starting from rest and you have a uniform acceleration, which is the case that we're going to have to focus on for the greater part of this chapter. I did want to show you one more time how this top equation can come into play as an alternate solution. If you take this equation, the displacement is the average velocity times the time. If we look at that last entry, that 55 meters, well, the time of 4.3 seconds, the distance is going to be your average velocity. Now, what is the average velocity? V average for that 4.3 second mark. So the time is 4.3 seconds, but what's our V average? Well, if you look at the table, from 0 to 4.3 seconds, look at the middle column, the speed. If you start at 0 and you end at 26 meters per second, your average speed is 13. So your displacement is going to be 13, your average velocity, average speed, times 4.3. Now that comes out to be 55.9, or in other words 56 meters. Now don't be alarmed that that's not 55, because that's simply a difference because of rounding from the 55 to the 56. It's the same answer, so don't let that concern you. But I mean, if the answer here came out to be 86, that would be a lot different than 55. But 55 and 56 have no significant difference. That's an alternate solution.